Hey everybody and welcome back. Or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And on this video what I'm going to go through is part 3 in this EVPN VXLAN series. Hopefully you've seen part 1 and part 2. In part 1 we touched on what is EVPN, what is VXLAN, what are the basic concepts around these two independent and different types of routing protocols. And in part 2 we focused more on all the many benefits that EVPN brings to the table. So I highly recommend you watch those two parts first, because in this part, in part 3, what we're going to start going through are the different types of EVPN or Ethernet virtual private network packet types that you can and will get in a EVPN network. Now there's actually 5 different types of EVPN packets and they all serve a different purpose. They all have a different function. And on this video what I'm going to go through is EVPN 2, which is about the MAC IP advertisement, and EVPN type 3, which is about multicast. I believe it's called Inclusive Multicast. And at this point you might be thinking, well, hang on Dave, you've missed out part 1. Where the hell is part 1? There is reason why I'm skipping part 1, and that is because the type 2 really serves as the main function, the main purpose of EVPN. EVPN is a control signaling protocol. It's signaling across the network who's connected to a particular VTEP, who's connected to a particular router. And that is the purpose of the type 2. Whereas the type 1 is more about when you've got a host which is multi-home. So I want to cover type 2 first, because as I said, it is the bread and butter. It's really the foundation on which EVPN is built. And when you have a type 2, you will have a type 3. They're just linked at the end of the day, even though they do serve different purposes. So I don't want to go into too much too quickly. Of course, we're going to go into more detail into each one of these packet types, into each one of these types of EVPN control protocols separately. First though, we're going to touch on the type 2, the MAC IP advertisement. And so let's start off with the root type 2, or the MAC IP advertisement. As I said, this is really the bread and butter. This is the foundations on which EVPN was built. Now, if you've watched the previous videos that I've done on EVPN and VXLAN, but more so EVPN in this case, you will know that EVPN is actually based on IBGP, or Internal Border Gateway Protocol. And it has something called Address Family Indicator, and this is addressed at with a value of 25, or I forgot the I there, AFI. And also within this, you then have a subsequent address family indicator, which has a value of 75. Basically, just know that together with this address family indicator and subsequent address family indicator, this details that within those update messages, this is EVPN, or Ethernet Virtual Private Network. And EVPN, because it's based on MPBGP, BGP at the end of the day, we are doing update messages of network layer reachability information, or NLRI. And as I've said in previous videos, in the network layer reachability information that's contained in those update messages in EVPN, we are advertising MAC and optionally, it is an option at the end of the day, IP addresses. And additionally, within these update messages, there are also path attributes such as origin, multi-exit discriminator, AS path, local preference, router ID. Needless to say, there's a lot of path attributes within that. And I just want to set the scenes on what EVPN is from a very high level point of view, and also what this network is that you're looking at before we go any further. So the network is very simple. We've got 2 spines. We've got spine 1 and we've got spine 2, and we've got 3 leaves, leaf 1, leaf 2 and leaf 3 over here. Now we've only got one user connected to leaf 1, and we've got user 2 connected to leaf 2, and then we've got a multi-homed or dual-homed server that's connected to both leaf 2 and to leaf 3. Now, in terms of this update on route type 2, we're going to be looking at it from user 1, or really from leaf 1's perspective. Now, when it comes to sending these update messages, these network layer reachability information, the MAC and IP addresses, when we're sending it to either leaf 2 or across to leaf 3, we can obviously do so via spine 1 or spine 2, because leaf 1 has a connection to both leaf 1 and across to spine 2. And spine 1 obviously has a connection down to leaf 3, spine 2 has a connection down to leaf 3, and it's exactly the same for leaf 2. And what I've also added in is the loopback addressing, or the LO0.10. This is basically a loopback interface, a logical interface that's configured in the Junos, and the leaf 1 loopback address is 10.10.10.1.1 being for leaf 1/32. For leaf 2, the loopback 0.10 is 10.10.10.10.2/32. And guess what? For leaf 3, it is 10.10.10.10.3/32. If you wonder where this .10 is coming from, that's because the users are all in VLAN 10. So user 1 is in VLAN 10, user 2 is in VLAN 10, and even the server here, which is multi-homed, is in VLAN 10. And that virtual network identifier is 5010 or 5010, however you want to pronounce it. So just a quick view on what the network setup is there. So now let's go into the route type 2, the MAC IP advertisement. So let's say, for example, user 1 sends a frame into leaf 1 and it wants to get to this destination over here. It wants to get to user 2. Now at this point, what leaf 1 is going to do is it's going to store the MAC address of user 1 in its switching table, in its MAC address table. Now using EVPN, which is a control-based protocol, it's a signaling protocol, leaf 1 is going to advertise over IBGP, over BGP, those update messages. It's going to advertise to leaf 2 and to leaf 3 that users 1 MAC address is contained or is connected to me. But obviously there's a lot of information that goes within this route type 2. So one of the first fields you'll see is actually a route distinguisher, or ID. Now the leaf 1 here is going to set the route distinguisher to be a type 1. If you recall, you've either got a type 0 or a type 1 route distinguisher. Now the type 0s aren't really used anymore these days. You commonly see the type 1 actually being used. And so the route distinguisher is actually going to first have the loopback interface, or the router ID, assigned as the route distinguisher. There's two parts to a type 1 route distinguisher. So first we're going to have the loopback 10.10.10.1 colon, and then it's going to have the VLAN, so or the VNI identifier. So in this case we're then going to have 10. So here we're actually identifying via the route distinguisher when leaf 2 or leaf 3 receives these update messages. Just by looking at the route distinguisher, it's going to be able to identify the route ID, i.e. it's come from leaf 1, and this is for VLAN 10. That is what route distinguisher essentially does, is it distinguishes all the routes and prefixes which are being advertised throughout the network through EVPN, through BGP, allows the receiving devices, the receiving routers, to distinguish what routes have been received and advertised by what routers that it has adjacencies to. Now the next part you will get in the type 2 advertisement is the Ethernet segment identifier, or ESI. The ESI identifies is the MAC address that's been advertised in this type 2 update a single homed connection like user 1 is and even user 2, or is it dual homed like this server, or multi-homed like this server? Now as I said, we're looking at it from the user 1's perspective, user 1 being connected to leaf 1. So this is obviously a single homed device. Now for single home device, you've got a 10 hex value. And that 10 hex value is all zeros. And so it would look something like this. I'm not going to draw all out, but you have 00 colon 00 colon 00 colon 00 colon, and you keep doing that until you have 10 hexes, obviously. But if it's a multi-homed like the server here, you would have a non-zero. So it could just be something like 11 colon 22 colon 33, etc., etc. You get the point. So if it's a single homed end device, it is all zeros. If it's a multi-homed end device, then you would have non-zero, so something like this here. But as I said, user 1 here is single home, so it is going to be all zeros that's advertised within this root type 2. And the next part that you get in the root type 2 advertisement, believe it or not, it is the VLAN identifier. This is basically the .1Q identifier. So we got VLAN 10 here, we got VLAN 10 here, and we got VLAN 10 here. So the value of the VLAN identifier is of course going to be 10. The reason why we're entering in the root type 2, what is the VLAN identifier, is as these update messages are sent from leaf 1 to leaf 3, either via spine 1 or spine 2, doesn't really matter, the receiving device needs to know, this update message, it's come from leaf 1, I can tell that by the root distinguisher, and it's a single homed device, but I've only got one route to get to that destination. That's what the ESI does when it's all zeros, it's single homed. But also now I can identify that this device coming from leaf 1 within this single homed connection, it's within VLAN 10. And do I have any devices that are actually connected in VLAN 10 as well that I need to de-encapsulate this traffic and send it onto? And this is the part which is optional, the IP address. It doesn't have to be sent in the root type 2. It is optional at the end of the day. So if leaf 1 is doing some kind of ARP spoofing, it's looking at ARP packets coming from user 1, and it sees the IP address I haven't entered in, but wherever the user IP address is of user 2, it can then advertise the IP address over to leaf 3 via spine 1 or spine 2. It's optional at the end of the day. Really, the bread and butter is the MAC address. And let's just say, for example, the MAC address of user 1, let's keep it simple, is AABBCC. And I know that's only the first 3 bytes. The MAC address is 6 bytes, but let's just keep it short, keep it simple. In the root type 2, you have got the MAC address of the device that's being connected. So in this case, we would have AA:BB:CC. So if we look at this root type 2 with just these values, these attributes which are within this advertisement, you can see it's quite a lot of information already. And this is why I say it's the bread and butter. We can see from leaf 2 or from leaf 3's perspective, when it receives this update message, we can see what the root distinguisher is. We can see it's come from the router with ID 10.10.10.10:1 with a 10 at the end for VLAN 10. We could see it's a single home device because it's all zeros. We could see that the device is behind VLAN 10, and I can check within my switching table and VLAN table, do I have VLAN 10? Optionally the IP address, but this device has this MAC address. And because in the enterprise, in the campus, and in the data center, VXLAN is commonly used alongside EVPN signaling, we then have the VNI, the VXLAN Network Identifier. And as you can see here, the VNI for all these users is 5010. So this is where we're taking that 12 bits that's for that VXLAN identifier, and that only gives you a theoretical maximum of 4096. But within a VNI, you've got 24 bits, which gives you just below 17 million network identifiers. So quite a lot, especially for data centers. It's very scalable. We then enter in this root type 2. What is the VXLAN network identifier for this root type 2? So in this case, it would be 5010. It's generally recommended that somewhere in that VNI you have that VLAN identifier, just for management purposes, just so you can keep some kind of management if it comes to troubleshooting. So that's why I've done 5010, 10 being the VLAN identifier and 5000 being it's above the 4096 that the VLAN can support a theoretical maximum up to. And of course, when leaf 2 or leaf 3 receives these update messages, these root type 2s, it needs to know what is the next, and I'm running out of space, next hop. So the next hop would be leaf 1's loopback address. So in this case, it would be loopback 0.10. Now, obviously, the MAC address, the next hop MAC address is going to vary hop to hop, point to point. So the MAC address from leaf 3 going to spine 1, the destination would be that of spine 2. And then from spine 2 to get down to leaf 1, the destination MAC address would be that of leaf 1. So that is obviously going to change at layer 2. But the next hop IP address that is contained within this root type 2 is that of the advertising router. So leaf 3 here would see the advertising router for user 1 as the loopback 0.10 interface. And what we cannot forget is something called the root target. Now the root target, you have an import and an export policy. And it will look something like this. You have the ASN number. So let's just say for this entire autonomous system, it's 6510 or 100, I should say. Just throwing out a number. So then the root target would be set to be 65100, and then you'd have an arbitrary number. So in this case, it's used the VLAN identifier 10. So the root target here identifies the autonomous system that this update message is contained in, and an arbitrary number here, i.e. the VLAN. Now the reason why you need an import and an export is because without this import policy, that receiving router is just going to discard those updates. The reason why you need an export policy is you need to export this policy into the update itself. So let's say from leaf 1 here wants to advertise this update message over to leaf 3. And it sends it, just for example, over spine 1. And it will set that export policy to have that value that I've just defined down here. I appreciate the screen's getting busy. I'll clean it up in just a second. But it exports that root target, which is an extended community of BGP. And over to leaf 3 it goes. And over here, you'd then import that update message. So you need the import policy to match that of the export policy. If it doesn't match, as I said, all leaf 3 is going to do is it's going to drop those packets, because the root target is identifying, is this of concern? Is this of interest to you? Is this of interest to the receiving router? Hence, if you don't have it configured and it's identical, then it will just drop those packets. And those are all the values. I've just tidied up the screen, but those are all the values, all the attributes that you get within the type 2. And this is why I said it's the bread and butter, it's the foundings, it's the foundations of EVPN. And just as a quick recap, the root distinguisher uniquely identifies what router is advertising, that prefix, that update message, and in which case it's set to be the leaf 1's loopback address. And then you'd have the VLAN identifier. So that would be 10.10.10.1 with that :10 at the end. And the next part is the Ethernet segment identifier. So for user 1 here, it is behind a single homed connection. So the ESI would be all zeros. If it was a multi-homed connection, then it would be non-zeros. It would be, as per my example, 11:22:33, etc., etc., etc. So ESI is allowing the receiving device, such as leaf 3, that's receiving these update messages, these root type 2s, to identify, has it got one path to get to that destination, or has it got two paths to get to that destination? And the VLAN, so here the root type 2 defines what VLAN is user 1 behind, VLAN 10 in this case. And that's advertised through, so leaf 3, using my just recent example, would know, to get to this device that's advertised with this from this root distinguisher, leaf 1, and it's a single homed connection, I can get to it through VLAN 10. Do I have any devices that are connected to me in VLAN 10 as well? And optionally IP address, this is optional for root type 2. It doesn't have to be there. It really depends on if leaf 1 is spoofing packets is learning the IP address. And then we have the VXLAN network identifier. So here, if I just build a tunnel from leaf 1 to leaf 3, and I do apologize for my lack of artistic skills, that's my drawing for a tunnel. Leaf 3, when it receives these type 2 packets, would know, if I want to get to user 1 through spine 2 or spine 1, doesn't matter, I would do so through the VXLAN tunnel 5010, which is defined here, as you can see. And then the bread and butter is MAC address, the MAC address of user 1. MAC addresses are defined at layer 2. Layer 2 is Ethernet. We are talking about Ethernet Virtual Private Network. EVPN is a massive protocol, but it sits within multi-protocol BGP. We are using BGP to advertise the MAC addresses of all these connected devices across the network over a routed backbone, such as the underlay, or as it's called, the underlay. So the MAC address is the bread and butter. That's really important here. And the next hop, leaf 3 needs to know, if I want to get from leaf 3 over to leaf 1, what is my next hop IP address? And as I said, that next hop IP address is going to be that loopback interface that is configured for that VXLAN tunnel, for that VNI. Without that, obviously leaf 3 or leaf 2, or doesn't matter how many leaves devices you've got, at the end of the day, it won't know what to use in terms of that destination IP address. And finally, the route target. We've got an export policy that leaf 1 defines. So first it's going to use the autonomous system number and then an arbitrary value. And that import policy on leaf 3 needs to be identical. It allows leaf 3 or leaf 2, etc. to know, when I've received this update message containing this network layer reachability information, this route type 2, with these path attributes, with this MAC address, maybe IP address, with this VXLAN identifier, with this ESI, etc. It allows it to, even before then, to identify, is this of interest to me? If it doesn't have that import policy that is configured and identical to that export policy, it drops the packets. If it does, it accepts the packets, and through the process it goes. And that is the route type 2 EVPN packet. That is how we can advertise MAC and maybe IP addresses across this EVPN network, or the EVPN virtual instance, EVI, and all the other attributes that are contained within that route type 2. And now we move on to route type 3, that is called the Inclusive Multicast. Now, I actually do disagree with this name. That is the official name for EVPN route type 3, because we aren't just talking about multicast here, we're actually talking about broadcast, unknown unicast, and multicast traffic. Obviously, we know the acronym BUM, broadcast, unknown unicast, multicast. So this type 3, yes, it's dealing with all aspects, broadcast, unknown unicast, and multicast. How is this different to the type 2 that we've just gone through? Well, in the last section, what we discussed was user 1 sent a frame up to leaf 1. Leaf 1 learns its MAC address and basically then advertises that learned MAC address along with the ESI, VLAN, VNI, next hop, route distinguisher, route target, etc. All those contents of the route type 2. It would advertise all of those attributes via the update message to both leaf 2 and leaf 3 so that they learn about user 1's existence. But this initial frame dash packet that's sent from leaf 1 to user 1 to leaf 1, that is a unicast packet. What happens when there is a broadcast packet or a multicast traffic or even an unknown unicast? Even though EVPN does very, very well because of the proxy op function, it does minimize the unknown unicast. So what happens when BUM traffic is sent from user 1 up to leaf 1? And that is, of course, where the type 3 comes into it. Now, there are actually two types of type 3 in terms of how we're going to handle the BUM traffic itself. We can do so with underlay replication, and also there's ingress replication. And obviously we're going to discuss what each of these actually mean, but first we'll actually start with the underlay replication and then move on to the ingress replication. So as I said, user 1 has sent in a bum traffic into leaf 1, and leaf 1 knows via that type 2 update message that has been sent and received from leaf 2 and leaf 3 that both of these leaves have users in VLAN 10 connected, single-homed or multi-homed. They have these users connected to the same VLAN 10, out there in the network, i.e. within the EVPN virtual instance, in the EVI. And that's learned via the type 2. So if you're wondering how does leaf 1 know that where to send this bum traffic to, it's learned it initially via the type 2, because in the type 2 header, we have the VLAN ID, and leaf 2, leaf 3 will learn that user 1 is in VLAN 10 over here, and when leaf 2 and leaf 3 send their type 2 messages, leaf 1 learns that user 2 is in VLAN 10 and the server here is in VLAN 10. And then we have that broadcast, unknown, unicast, multicast traffic coming in. And typically this does depend on vendor. There's two ways to handle and forward this bum traffic. So first let's go through the underlay replication. And what we're actually referring to when it comes to underlay replication is PIM, or Protocol Independent Multicast. Now, to be honest, I'm not a fan of PIM. I'm not a fan of multicast technology. It's complicated, but it's great. It really, really works. But when it really doesn't work, you know about it. However, so I'm not going to go into multicast because I need to learn more about it myself at the time of me doing this video. But what we have when it comes to underlay replication is, say the spine here is that rendezvous point, or RP as it's known. And we know that leaf 2 and leaf 3 have hosts, user 2 and the server here have these devices connected, and they are in the same VLAN. So with the underlay replication, first let's talk about the underlay. We have the underlay here. So here we're actually referring the layer below EVPN, the layer below the overlay, and this is where we'd be running some form of IGP like OSPF, ISIS, whatever it actually is. It really doesn't matter. But what happens, and I'm just going to get a different color, is leaf 1, it wants to send some form of bum traffic to leaf 2 and leaf 3. It would send that copy, a single copy of that bum traffic to the rendezvous point up here, and at which point the rendezvous point, the spine 1, will replicate that single packet and send it down to both leaf 2 and to leaf 3. But in such a small network, it's on the diagram, that's not really that significant. But if you think about it, if we've got another leaf here and another leaf here and another leaf here and another leaf here, etc., and this is leaf 4 and this is leaf 5 and this is and say this is now leaf 31. So in total we've got leaf 1, leaf 2, leaf 3. So we've got 31 leaves in total. We have only sent one packet, one copy of that bum traffic up to spine 1, which was that rendezvous point, and then it sends it down to leaf 2, sends it down to leaf 3, sends it across to leaf 4, to leaf 5, to leaf 6, 7, 8, 9, 10, all the way up to 31. And the efficiency of this is significantly better versus ingress replication. I just want to make that clear. The reason why this is significantly more efficient in terms of bandwidth is because, say that this packet that's gone from leaf 1 up to the spine is an ARP, just for example. I'm just going there, and say it is 100 bytes. Now we only have one of these packets, so 1 times 100 bytes. And the rendezvous point, spine 1, is then going to send a copy of this. It's going to replicate this packet another 30 times to send to leaf 2, to leaf 3, to leaf 4, 5, 6, all the way up to leaf 31. Obviously, it's not going to send it back to leaf 1, hence there's only 30. So now we're going to do 30 times 100 bytes, which gives us 3 kilobytes or 3,000 bytes of actual overhead that's going over or under or through the underlay, depending on which way you want to think about it there. So that is very efficient. It sounds like a lot, but for a data center, that's nothing. That's even for an enterprise network, 3 kilobytes is absolutely nothing. When you see in a few minutes time how this is seen from an ingress replication point of view, you'll see why this approach using PIM as that type of management of bum traffic is so much more efficient. And actually, let's do that now. Let's actually talk about what is ingress replication. So with ingress replication, what the leaf is doing is we're actually a replicate of that bum traffic that's been sent in from user 1 or host 1 or whatever the device is, and we're replicating that to send onto leaf 2, onto leaf 3, onto leaf 4, etc. And I'll just draw them again. Here we've got leaf 4, leaf 5, leaf 6, and eventually we've got leaf 31 on the end here. So leaf 1 is sending and replicating a copy of this bum traffic here to leaf 2, to leaf 3, to leaf 4, to leaf 5, to leaf 6, 7, 8, all the way up to leaf 31. But with ingress replication, we are not using multicast, we're not using PIM. We don't have this concept of a rendezvous point. There's none of this, there's no shared tree. So leaf 1 is going to send 30 copies of that broadcast unknown unicast multicast traffic to spine 1. It's also going to do the same over to spine 2. So another times 100 bytes or 30 times 100 bytes over here as well. And guess what? At which point spine 1 and spine 2 will forward it down to leaf 2, forward it down to leaf 3, forward it down to leaf 4, 5, 6, all the way up to leaf 31. So if you just do the quick maths there, 60, because we got 30 here and 30 replicates here, 60 times 100 bytes then gives us 6 kilobytes of overhead. With the underlay replication, we had half of that. Now, it doesn't sound like a lot, and that's not a lot, especially for a data center, but this is just for one packet. This is just for one broadcast or unknown unicast or multicast traffic that's come in from user 1 up to leaf 1. That's nothing. What if you've got 100 frames or 100 packets per second or maybe more of bum traffic just coming into the same leaf? You can see how this then scales up and how ingress replication then has less efficiency when it comes to bandwidth versus the underlay replication. So why on earth would anyone choose the ingress replication? And there is one word here that really describes it for me, is simplicity. Multicast is complex in terms of protocol independent multicast, the shared tree, the rendezvous point. That is a massive topic in itself. It's something I've not gone through yet on this channel, but I will do eventually. With the ingress replication, we're not doing PIM, we're not doing shared tree, we're not doing rendezvous point, and with the underlay replication, you can have a different shared tree and a different rendezvous point for each VNI. So it becomes extraordinarily complicated. And then if there's a problem, you've got to then troubleshoot that multicast tree. So you need a lot of expertise. Whereas with the ingress replication, we're not doing PIM, we're not doing RP, as I said, no shared tree. And as such, it becomes a lot easier to configure, a lot more easier to manage, a lot more easier to troubleshoot, which is why in the Juniper Juniors world, at the time of me doing this video, only ingress replication is supported because it's more easier to adopt. It's easier to get up and running when you've got EVPN and VXLAN deployed in your enterprise campus and data center network. But what is contained in the root type 3 message? Well, of course, we have the network layer, and let me try that again. We have the network layer reachability information, the NLRI, i.e. the prefixes that can be reached, or the prefix that can be reached, and the path attribute associated to it. And just like the root 2, the EVPN root 2 type, we've also got a root distinguisher, which will be a type 1 again. We've also got a root target. The receiving device has to have the same root target that's defined on the import policy as the export policy. So that would be something like 65100:10 as the root target. We would have the tag or the VLAN identifier. So this would be 10, which is I've just put in brackets here the VLAN itself. Next hop IP address, just like in the EVPN route type 2. But what is different, we don't then have a MAC address in here. We don't have an IP address in here. That is contained in the EVPN route type 2 that we've gone through. But there is then this PMSI, which stands for Provider Multicast Service Interface. And just so you know, the PMSI defines quite a few different things. So I'm just going to do PMSI up here. So first you've got flags. Now at the time of me writing and doing this video, only one flag is actually defined, and that is who's originating this PMSI, who's originating this route type 3. So that would be leaf 1 in this case. But you'd also have within here the tunnel type. So here you'd have ingress replication, so I'm just going to write IR there, or you'd have underlay replication for that shared tree, RSVP, etc., etc. There's many components actually that go and are defined in the tunnel type for underlay replication. It's not just PIM, there's actually quite a few in there. But here we actually just define in the PMSI, are we using ingress replication where the leaf makes a replicate of that bump traffic and forwards it on, or are we actually using the underlay to manage that bump traffic? And also at the end, you've got the tunnel ID. The tunnel ID is that multicast group. So if you think about OSPF, that would be 224.0.0.5 or .6, etc. So that is that multicast group that is used for that tunnel ID. So let's finish this off with an example. So again, let's say leaf 1, user 1, sorry, has sent some kind of bump traffic, whatever it is, doesn't matter, up to leaf 1. And it's destined for all hosts, so it'll be a broadcast, for all hosts, user 2 and the server that are in the same VLAN here. Now using the underlay replication, or UR for short, leaf 1 would send a single copy up to spine 1, and then because that is the rendezvous point, then spine 1 would send a replicate of that copy down to leaf 2 and across to leaf 3, leaf 4, leaf 5, etc. Done. But obviously all of this is managed by protocol independent multicast, or maybe it's RSVP, or maybe it's PIM sparse mode, etc., etc. All of this, as I just said, is defined within that PMSI attribute that's contained in that type 3 overhead. But regardless of the type of multicast protocol or means, we're using the underlay here for leaf 1 to send a single copy of that broadcast, unicast, multicast traffic from user 1, and then that rendezvous point is making all the duplicates necessary and forwarding it on to all destinations, all users that are in that same VLAN. When it comes to ingress replication, on the other hand, we aren't doing rendezvous point, we aren't doing RSVP, we aren't doing sparse mode, there's none of that. But we still, user 1 is sending some kind of bump traffic in VLAN 10 to all hosts in VLAN 10 as well. And at this point, leaf 1 is making a duplicate of that bump traffic, and it's sending it on to leaf 2, it's sending it on to leaf 3, it's sending it on to leaf 2, it's sending it on to leaf 3 via all the spines that it actually has connected to it. So that there is literally the difference from a very high level working example between the way EVPN handles multicast traffic, broadcast, unknown unicast, multicast traffic to be specific. We've got the underlay replication, and then we've got the ingress replication. Again, depending on vendor, it will vary. You might have underlay replication. In the Juniper Junos world, again, at the time of doing this video, there is only ingress replication supported because it's easier to get along with. Underlay replication is just more complex by its very nature. And so there we go, everybody. That is the end of this video. That is the end of this part 3 in this series about EVPN and VXLAN routing and tunneling respectively. And we've actually started to go into a bit more detail now into the EVPN route types, specifically the route type 2 and the route type 3. And just as a quick recap, as a quick summary, the route type 2, as I've said, is the bread and butter. By the way, if you don't know what that means, it means it's the foundations, it's the building blocks, it's what generally makes, to some extent, EVPN work. In the route type 2 EVPN message, We are sending MAC addressing. We're sending MAC addresses of those connected devices, whether it be a laptop, terminal, server, doesn't matter. It will have a MAC address, and we're advertising that over the underlay through EVPN and to remote peers that are connected to the network. And we're also advertising inside that route type 2, the route distinguisher, the route target, the ESI, is it single-homed, multi-homed, as well as other attributes like the optional IP address, next hop, etc. So the route type 2, very important when it comes to learning what layer 2 device is connected to where in the network. And again, EVPN is a great signaling protocol to allow that to happen. And then we've got the type 3. We need the type 3 because the type 2 is unicast traffic. It's a host sending a unicast packet and the device just advertises, hey, this MAC address is connected to me. Here you go. All remote peers, this is who I've got connected to me. But what happens when there's bum traffic? That's where the type 3 comes in. It identifies what type of management am I doing for bum traffic. Is it underlay replication or is it ingress replication? Underlay replication is using some form of PIM, whatever it may be, whereas ingress replication is where the leaf, the originating leaf device, makes a duplicate, a replica of every single packet and forwards it on to all peers that are interested in that packet, that are connected to that same virtual network identifier. So as always, I hope you found that useful. I hope you found that informative. If you like this content, if you like what I've gone through, please give me a thumbs up. It's the best way to support my channel. Any questions or comments, please let me know down in the comments box. I love the feedback I am getting. Other than that, stay tuned for part 4 where we're going to start going into more detail the ESI, and that's going to be the EVPN route type 1 and what is the EVPN route type 4. Other than that, thanks for watching and goodbye.